burst, and also we have some initial result for burst, and now we have the future expected science case with burst. Let's welcome Tetsuya from Cosmology to talk about this.
Okay, thank you very much. I really appreciate the organizers for giving me this opportunity. So today I'm going to talk about the expected science cases with burst. So I'm Tetsuya Hashimoto from National Johnson University. This talk is in collaboration with these people, including Wei, Mintan, Fishing, Jiu, Tomo-san, JP, Kayan, and Surin, Yapan, so many people, Surida, and the rest of collaboration people. I really appreciate their collaboration. Thank you very much. I just took a picture from our Nanto station, outrigger station. Okay, so let me get started. So this is the outline of my talk today. So I start with, again, I would like to emphasize the advantage of burst projects, and then I really focus on expected science cases using burst. But actually, my talk is about selected science cases. Actually, we can do more than this, I believe. Then let me summarize at the end of my talk. I think Sujin and Surida, so they give a very good introduction to fast radio burst. I quickly go. So fast radio burst, FRB, is a mysterious radio signal. Most of them are coming from galaxies outside Milky Way. The problem is, so we don't know what they are. So therefore, we really want to identify the progenitors of FRBs here. Understanding the origin of FRB is one of the most important missions in astronomy and astrophysics. This has been mystery because there were 3 challenges in previous radio observations for FRBs. As Suri-san already talked about, let me briefly repeat again. So one challenge was poor localization capability. So now they can detect many FRBs, but because FRB disappear within 1 millisecond, it's really hard to identify, localize, accurately measure the position of FRBs on the sky. So typical positional error on sky is the arc minutes level. In this case, I am saying 30 arc minutes or so. Inside of this large error sample on sky, there are so many candidates for FRB progenitors, so there is no way to identify. So to overcome this problem, we will conduct BLBI observations using burst. Then we should be able to achieve this localization capability down to 1 arc second level, or even better, as mentioned by Surida. In this particular case, we can only see single astrophysical source inside this radio sample. So that means we can really identify the origin of FRBs. So we have to do this. The second challenge was the poor field of view. So traditional radio telescope, has a limited the size on sky that you can observe at single time, field of view. So this is again schematic diagram. If you have a very limited field of view on sky, so you can only detect FRBs happen inside the field of view. If FRB happens outside this field of view, so in principle there is no way to detect such FRBs. So that means there must be significant amount of missing FRBs so far. So we really have to detect all of them. So then using this burst, so we should be able to expand our field of view up to 10 to the 4 square degree, which is nearly all sky. And the third challenge, as Suri-san mentioned, let me repeat again. This is a mismatch between previous FRB observations and GW observations. So one of the major scenarios is neutron star merger for the FRB origin. Then we do expect possible association between GW event and FRB event. Then now many people started to pay attention to this possible association. But so far, no, there is no conclusive answer. This is because there is a mismatch. So if I simplify situation, GW detector is sensitive, that's all sky sensitive, but their distance is kind of limited. But previous FRB telescopes, they really focus on FRBs using very narrow field of view. Then they observe very distant universe. So there's an inconsistency between the survey volume between FRB and GW observation so far. There's not much overlap here. So therefore, to overcome this problem, we focus on 10 times closer to the universe using extremely wide field of view of this burst telescope, so that we can maximize the chance of the simultaneous detection between GW and FRB events. Okay. Then, to overcome these three challenges, we came up with a new design dedicated for detecting FRBs, which is Bustling Universe Radio Survey Telescope in Taiwan. First, PI is very bad, again. As Suri-san mentioned, so we use this kind of fishbone-like radio antenna, which can achieve very large field of view on sky. And we already finished this deploying the 256 antennas in mid station. And also we deploy these antennas in different places in Taiwan or even in international partners to achieve accurate localization capability doing this VLBI observations. I believe this figure is really clearly highlighting the uniqueness of this burst telescope. So x-axis is a wide field of view of different radio telescopes as a function of sensitivity or maybe effective area, size of the telescope. That's maybe easy to explain. If we go to left, actually this is better, larger in this axis. As you can see, burst is really outstanding in this parameter space. If I compare with CHIME, which is current most powerful FRB radio telescope, actually we do have more than 10 times better field of view. If I compare with similar project which has also whole sky capability, very large field of view, their sensitivity is 3 order of, or maybe I have to say, so our sensitivity first is about 3 order of magnitude better than our previous whole sky instrument. Actually, these instruments is very hard to achieve extragalactic FRBs, which is actually majority of FRB sample now. So this telescope will be really the first FRB telescope which has both localization capability and extremely wide field of view. So that's why we really expect Taiwan will lead the FRB science in future. Then let me talk about science cases here. I would say most significant science case would be this direct identification of FRB progenitors. Actually, there was only one successful case so far. So there was very apparently blind FRB happens in 2020, and then this TIA2 and the CHIME, they detected this apparently extremely blind FRB. Then they localized this down to this region. But this region was still large. Then they were not able to localize even further. But now this is the first telescope in China. They conducted follow-up observations to find significant activity of galactic magnetar. So this was only one successful case that they really identified the origin of this FRB. Actually, this apparently blind FRB happens inside our Milky Way. And the projector was this magnetar, active magnetar, in our Milky Way. But so far it is limited to only one case. The main reason is, one reason would be, you can imagine this is actually very expensive observations because they really need to combine different radio telescopes here to find one projector. But now, after burst, we'll start science operation. All of these things can be done by using only single instrument, which is burst, because burst has both wider field of view and localization capability at the same time, simultaneously. Therefore, we expect we can increase this kind of direct identification of progenitors in future. Second case is about complete census of nearby FRBs. This is also very important in FRB science. Let me a little bit explain. There are two different types of FRBs. One is repeater and another is non-repeater. Repeater is repeatedly emitting FRB emission from the same source. The non-repeater is only single time from the same source. So separating these two different populations is very important in FRB science because naively speaking, people expect different origins for repeater and non-repeaters. But there is an observational problem here. past radio observation has always limited amount of time, so that means time window is always limited. In this case, this is truly repeating FRB, but we can only observe this time window to detect a single pulse. In this case, we misclassify this as non-repeaters, so this is always a problem. Due to this problem, we even don't know the true number fraction between repeater and non-repeater, and also we don't know true repeating rates too. Even so, this is a fundamental question here. So to overcome this, we really need long monitoring observations with high cadence. That can be achieved by burst. So burst will really address this fundamental question, probably for the first time. Because burst has about 25 times larger field of view than chime. That means burst also has about 25 times longer continuous observation time for each source than chime. Our time window is very large. The last science case will be EKB counterparts. This is very important. As I mentioned, maybe GW counterparts will be the key to understand some of EKB progenitors, I believe. Actually, there's a prediction here, model prediction, possible association between GW and EKB. There was actually paper reporting possible association. Okay. And then another point is multi-wavelength observations is important. So we can identify host galaxy using multi-wavelength observations, follow-up observations. So far, only identified host galaxies are limited to only 40 samples, but we should be able to localize about 100 FOBs per year. So we expect we can expand more samples in future. Then this allows us to conduct physical environments or progenitor types. And then this is also very important. Simultaneous multi-wavelength counterparts is very important because just by looking at the radio, it's very hard to tell different physical models for FRBs because all of the models are designed to explain radio emission. So we have to go to the multi-wavelength counterpart to differentiate between different models. I'm sorry, I don't have time to explain this, but multi-wavelength observation is very important. And the last but not least, this is my personal expectation. Actually, the story doesn't end here. Actually, it's not only for original FRBs, but using FRBs, we can address some key questions in astronomy and astrophysics. So, for example, say where is missing baryon or cosmic expansion, say Hubble tension problem. And then actually our students, Tsuyin and John Kainin, they provide posters in this conference. So therefore, if you are interested, please visit their posters. I have time a little bit. Okay, I summarize. FRB science is really exciting. And then burst is really unique radio telescope. This will be the first FRB telescope that has both localization, wide field of view capabilities. And then burst will lead the revealing the origin of FRBs. Okay, I stop here and then take questions. Thank you very much.
One quick question. Just a minute.
Thank you. So you emphasize that your telescope which has a much higher sensitivity than your existing telescope. So I was just wondering, maybe I missed, but I was wondering what's the main factor to increase the sensitivity?
Okay. If I compare to these guys, yes, sensitivity is actually high. I think the main reason is we have more antennas, simply. So they have very few antennas deploying, but we have more than 100 antennas. This is our main reason difference.
Since we are a little bit behind schedule, so let's discuss the GIA.